Welcome to the Univa webinar, 10 cool things you may not have known about Univa Grid Engine. My name is Andy Schwerscott. I'm Strategic Initiative Manager and I have a services role for our customers. Univa is a workload management vendor and many people know us for almost 9 years as the Grid Engine company. We focus on enterprise scale HPC automatization workload management software and help our customers to boost revenues, reduce costs and cycle times by helping them to make their engineers and scientists more efficiently using the HPC data center resources. Univa has more than 250 customers, 85 are among the global 2,000 companies. More than 3.3 million cores are under management of Univa Grid Engine. We operate the biggest HPC clusters in the world and proved that Univa Grid Engine can operate a more than 1 million core cluster in a cloud environment. Our customers come from a number of different industries. We have a strong leadership position in life sciences, 10 of the 10 largest actually, and more than 60 overall. We got a strong EDA base, 2 of the 3 large EDA ISVs use Univa Grid Engine. We got some of the world-leading largest oil and gas organizations, and dozens of airlines use Grid Engine to optimize their fleet logistics. Grid Engine has been our main product line for a long time. Customers use the software for workload management based on policies to efficiently utilize their HPC data center resources, getting the right workload done for the right people in the right time. Our customers run their Grid Engine-driven clusters in excess of 70 to 90% utilization, helping them to speed up development cycles and bringing down the cost of their hardware and software investments. NavOps Launch is now helping our users to migrate Grid Engine workloads into the cloud in a very seamless fashion. It works alongside Grid Engine and allows operating Grid Engine in hybrid cloud environments, meaning an on-prem cluster is dynamically expanded with execution nodes in the cloud and in cloud-native environments, where a self-contained Grid Engine cluster is deployed in the cloud. NavOps Launch supports budget and access management to ensure cloud costs do not run out of control and can be charged back to the end users. So now let me get started with the 10 cool things about Univa Grid Engine. Advanced container support. Univa Grid Engine supports Docker and Singularity containers. We have a seamless support for Docker workloads by having a tight integration through a so-called container shepherd, which allows for Docker interactive jobs, Docker batch jobs, Docker service containers, containerized parallel applications, and GPU-enabled containers provided by NVIDIA. The integration provides full resource enforcement, for instance memory and runtime limits or device mappings are enforced, and it has detailed usage records in the accounting database. When the job is over, we guarantee a reliable container cleanup and deletion. For administrators, it's very important that Docker jobs run as the job user, not as privileged user root. That means administrators don't need to add users to the Docker Unix group, and there are no security concerns about root containers. Singularity containers run out of the box. We also have support for NVIDIA Docker containers. We published a couple of blog articles on blogs.univa.com where we describe how to integrate Univa Grid Engine with Docker, with Singularity, and with NVIDIA Docker containers. So as a takeaway, Univa Grid Engine integrates container workloads seamlessly with traditional workloads. There is no need to have dedicated container hosts. You can mix traditional workloads and Docker workloads and Singularity workloads on the same machines. Scalability and throughput. That's a multidimensional challenge. The number of machines and cores is growing, the number of running and pending jobs is growing, and naturally the number of jobs running per hour, per day or per month is growing. Today, Univa Grid Engine operates the biggest HPC on-prem clusters. We have more than 6,500 machines in one single cluster with more than 200,000 cores. Our customers run 8 million more tasks per day, which means that's on average 90 jobs per second during a whole day. Grid Engine can support a sustained dispatch rate of up to 100 to 150 jobs per second. Time is money. speeding up a legacy workload by factor 60 requires the most scalable workload management system available. Western Digital ran 2.5 million tasks in a 1 million core cluster in just 8 hours, which ran 480 hours before. Also about this one we have an interesting press release. Univa Grid Engine has up to a 9 times higher throughput than the open source SunGrid engine. SunGrid engine can have a huge performance loss under high load. Also for this we have a technical brief available. Generally you can say that Univa Grid Engine easily achieves a 2 to 3 times higher throughput in many scenarios compared to SunGrid engine. GPU support. GPUs became almost a commodity in HPC data centers since they started 9 years ago. Today we see a widespread use of GPUs across all industries and use cases in machine learning, deep learning, artificial intelligence, mechanical engineering, financial services, biotechnology, and so on and so on. Our customers expect a solution that they can optimally use those expensive GPU resources. The key requirements from our customers are, of course, to get the highest possible utilization. Customers want to be able to mix GPU and non-GPU workloads on one single machine. They want to get optimal application performance and conflict-free access, so that jobs from one user cannot access the wrong GPU cards where another job is running. Naturally, there is also a need to support containerized GPU workloads and, last but not least, also reserve GPUs for exclusive use in specified time windows. Several Univa Grid Engine features form a comprehensive solution to utilize GPUs. We have resource maps. They are an extension to the Univa Grid Engine complex attributes and helps the scheduler to decide and maintain which GPUs a job uses. Automatic detection of installed GPUs and GPU types are done through an interface to the NVIDIA Data Center GPU Manager. That also helps us to do a proper topology detection, where we can report the type of the GPU, power usage, CUDA version string, and of course the affinity. This helps us to do topology-based GPU job scheduling, including NVLink support, to get the maximum job performance for serial and parallel GPU jobs. With the cgroups device support, we can only make the selected GPUs visible to the job. We also support shared GPU access, that multiple jobs can use one GPU. All of these details about the selected GPUs are also passed to the Docker containers. And advanced reservations can be used to create reservations for GPU jobs. So in summary, GPUs are a key resource of the HPC data center, and Univa Grid Engine optimally supports to manage and runs GPU workflows. Robustness and diagnosability. End users often ask why my job is not being scheduled. That seems to be a simple question, but often the answer is pretty complex. Many improvements went into Univa Grid Engine to better summarize those questions. We completely reworked the job dispatcher information. It now works better, works faster, and has less memory overhead. The benefits for the end users and administrators is that there is a better understanding of resource bottlenecks now possible. End users need less assistance by the administrators, and that supports in the end a more efficient use of the cluster. What went wrong? As we all know, things can go wrong in a HPC environment. There can be full file systems, network card errors, hostname resolution issues, failing machines, and so on and so on. Users and administrators wish a means to analyze the root cause of failing jobs. The benefit is that finding and repairing job and infrastructure issues is now faster. We can make the root cause of failing job information persistence after the job end, and we enable end users to self-diagnose job-related issues. Where does the scheduler spend its times? We provide detailed scheduling profiling, where each step of a scheduling run gets a detailed log entry. The benefit is that administrators can understand if or if not scheduling in Grid Engine can be a bottleneck, and it provides hints how to optimize scheduling policies. And it can provide useful information about infrastructure bottlenecks as well. Do I need to optimize my infrastructure? For this, we added lots of profiling information. There is profiling of various queue-master threads now possible. There is profiling for the request processing time available, and we can log the amount of data going in and out at queue-master. We also support logging for spooling times. The benefit is that bottlenecks can be better identified, and users and monitoring tools which might hammer queue-master in an unreasonable way also now can be much better identified. Cloud integration and bursting. NavOps Launch manages 5 key metrics critical for cloud computing: cloud cost, resource utilization, cluster queue status information, current workload consumption, and the workload characteristics. NavOps Launch supports a hybrid cloud setup, which allows to expand the Grid Engine cluster seamlessly into cloud environments. NavOps Launch also supports dedicated cloud setups, where Grid Engine clusters are solely integrated into cloud environments. NavOps Launch supports adapters for AWS, Google Cloud Platform, and Microsoft Azure, and any combination of those cloud providers at the same time is supported. Job classes. With job classes, users and administrators can manage complex applications and job submissions in a so-called job class object. Administrators or expert users create and modify job classes. This remedies the end users from understanding details how acceptable job submissions should be done. It also allows to control how end users can override predefined defaults in a job class. Each of the queue submission switches and resource requests can be either enforced, it can be marked as changeable, or it can be marked as deletable, or any combination of it. What are the use cases? For instance, MPI job submissions with core binding and memory requests can result in a pretty complex command line, or complex Docker command lines can be hidden in a job class. And last but not least, GPU job submissions with Affinity-based scheduling options also best are put in a job class. An example here, for instance, is the request for full nodes in heterogeneous clusters. A simple job submission is shown here, qsub-jc tensorflow.speech, and then the respective arguments to this TensorFlow jobs are passed. Enterprise level features. Grid Engine has an extreme scalability. More than 200,000 cores in production environments on more than 6,500 machines, and we have proven more than 1 million cores in a cloud environment. We have a low latency scheduler. The Grid Engine scheduler can sustain 100 to 150 jobs per second dispatch rate, and Grid Engine can accept more than 1,000 job submissions per second. We added a native Microsoft Windows support, so our customers can easily add the Windows host to an HPC cluster. Unisight is our comprehensive reporting and monitoring console. With Unisight, customers can analyze resource utilization and bottlenecks and can make the right decisions for the next investment cycles. All of the product features are owned and supported by an experienced worldwide Univa support and engineering team. There is a single ownership for all of our products by Univa, and we provide a single point of contact for our customers. Scheduling policies. We made improvements to the shared tree and functional policy algorithms. We have a fair prioritization of future rate jobs. For the shared tree, we added also support for fair handling of big parallel jobs compared to small parallel jobs or serial jobs. The shared tree now can handle arbitrary resources for past usage computation in any combination, such as wall clock, software licenses, GPU usage, resident set size, or any other consumable resources. The fair urgency policy supports a fair interleaving of jobs requesting different urgent resources. The affinity and anti-affinity scheduling supports to direct and flock jobs to well-suited node, for instance because certain nodes have certain data available, or the anti-affinity supports to disperse jobs to different nodes, for instance to distribute heavy I/O load. The SG-Sharemon utility can be used to monitor the shared distribution in the shared tree. Core and Numa Binding, Affinity scheduling. Univa Grid Engine detects and reports machine topology. We detect the NUMA nodes and the NUMA memory, the socket, cores and threads and cache sizes. GPU cards coupled to the NUMA nodes are also detected and correctly assigned. That information can be used to bind application to sockets and cores and NUMA memory. This can lead to a dramatic application performance improvement because we have best CPU caching. The operating system kernel does not need to schedule a process between cores and sockets, and we support co-placement of mixed CPU and CUDA GPU jobs on the same NUMA node. To achieve this, we also added new core binding strategies such as pack sockets, one socket per task, balance sockets, and so on. Affinity scheduling. Affinity scheduling is a job placement policy. Resources are defined by an administrator with an affinity or anti-affinity, and when jobs are requesting resources with a non-zero affinity, they will attract or repel other jobs on the same machine. Here is an example about the topology, how we detect it on a system. As you see, we detect the architecture, number of cores and sockets and threads, number of NUMA nodes, the topology, the cache sizes, the NUMA memory, and so on and so on. And at the bottom you see here also the information we provide about the CUDA devices. At the very bottom you have a sample submission line which shows how, for instance, a user would submit a hybrid MPI OpenMP job. In the example here you see the user requests 8 MPI tasks in total. Each of the MPI tasks should get 2 cores, and for each of the MPI tasks the user is requesting 2 GB of memory. Our advanced APIs. The configuration API is a comprehensive Python-based SDK to load and store cluster configuration. This allows to manage configuration as a software-defined HPC infrastructure. Customers can use the G-SaltStack as a backend automation software. This helps to easily roll out new clusters, make changes and archive configurations. The code for the configuration API is available on GitHub. For a long time we have the Drama version 1 API, for which multiple language bindings exist. We added in Univa Grid Engine the Drama version 2 API, which is a heavily modernized, much extended version of the old Drama API. The Python binding is on GitHub available. We added to Univa Grid Engine a REST API. The REST API gives full access to all configuration objects, cluster states, running and pending jobs. We support various language bindings for the REST API. In this webinar, I showed you the top 10 reasons why Univa Grid Engine is a leading job management software to manage critical workloads in modern HPC clusters, be it on-prem, in the cloud, or both together. Thank you very much for watching this webinar. This is Andy Schwirscott at Univa.